What happens to information when it falls into a black hole? This isn't just an academic curiosity. It's a question that threatens to break physics itself. Because if black holes truly destroy information, then one of the most fundamental principles we've discovered about the universe, that information is never lost, simply cannot be true. And yet, if information isn't destroyed, where does it go? The answer might be stranger than destruction. Black holes might not be cosmic garbage disposals erasing things from existence. They might be hiding the universe in plain sight, encoding everything that falls into them on their surfaces in ways we're only beginning to understand. Let's start with what a black hole actually is, stripped of the dramatic imagery. A black hole is a region of spacetime where gravity is so intense that nothing, not even light, can escape once it crosses a boundary we call the event horizon. This happens when enough mass gets compressed into a small enough volume that the curvature of spacetime becomes extreme. It's not a hole in space. It's not a portal to another dimension. It's a consequence of general relativity, the theory that describes gravity as the curvature of spacetime caused by mass and energy. The mathematics of general relativity predicts that if you compress enough mass into a small enough region, the escape velocity at a certain radius exceeds the speed of light. Since nothing can travel faster than light, nothing can escape from within that radius. That's the event horizon. It's not a physical surface. There's nothing solid there. It's simply the point of no return, the boundary beyond which all paths through space-time lead inward toward the singularity at the center. Now, here's where things get interesting. According to classical general relativity, once something crosses the event horizon, it falls inevitably toward the singularity, a point where space-time curvature becomes infinite, and our equations break down completely. Everything that falls in, every particle, every bit of matter, every photon, gets crushed at the singularity and seemingly ceases to exist in any meaningful form. The black hole grows slightly more massive, and that's it. The details of what fell in, its composition, its structure, its history, all of that information appears to be gone forever. This bothered physicists immediately, but for decades it seemed like a problem we could live with. Black holes were exotic objects, theoretical curiosities that might not even exist in nature. But then we found them. We found stellar mass black holes formed from collapsed stars. We found supermassive black holes at the centers of galaxies. We've now even photographed the shadow of a black hole's event horizon. They're real, they're common, and they're actively swallowing matter all the time. And that's when the information problem became unavoidable. In quantum mechanics, information is conserved. If you know the complete quantum state of a system at one time, the laws of physics allow you to calculate its state at any other time, forward or backward. This is called unitarity, and it's absolutely fundamental to how quantum mechanics works. It's not just a convenience or an approximation. It's built into the mathematical structure of the theory at the deepest level. But if black holes destroy information, then unitarity is violated. You could have two completely different objects, say a star made of hydrogen and a star made of carbon, both collapse into black holes of the same mass, charge, and spin. According to classical general relativity, these black holes would be absolutely identical. There would be no way, even in principle, to tell them apart. All the information about what went into making them would be gone. And that's a direct contradiction with quantum mechanics, which says that information must be preserved. This is called the black hole information paradox, and it's been one of the central problems in theoretical physics for over 50 years. It's not a minor technical issue. It's a fundamental conflict between our two best theories of physics, general relativity and quantum mechanics. One of them has to give, or both of them need to be modified, or we're misunderstanding something profound about how they fit together. The first major clue came from a discovery about black hole thermodynamics. Black holes have temperature. This sounds bizarre because we think of black holes as completely black, emitting nothing. But when you account for quantum effects near the event horizon, black holes actually radiate particles through a process we now call Hawking radiation. Virtual particle pairs constantly appear and disappear in empty space due to quantum fluctuations. Near the event horizon, one particle can fall into the black hole while the other escapes, and from the outside, this looks like the black hole is radiating. The temperature of this radiation is inversely proportional to the black hole's mass. Stellar mass black holes have temperatures far below the cosmic microwave background, so they actually absorb more radiation than they emit. But smaller black holes are hotter, and a black hole left alone in empty space would very slowly evaporate through this radiation, eventually disappearing completely in a final burst of energy. This makes the information problem even worse. Not only does information seem to disappear when things fall into a black hole, but the black hole itself eventually evaporates away, leaving nothing but thermal radiation that appears to carry no information about what went into the black hole. It's as if you burned the encyclopedia and tried to reconstruct the text by measuring the heat of the flames. The information seems irretrievably lost. But here's where the solution begins to emerge, and it's subtle. Black holes have entropy. Entropy is a measure of the number of possible internal states of a system that all look the same from the outside. For most objects, entropy is proportional to volume. A box twice as big can have roughly twice as many particles arranged in roughly twice as many ways. But black hole entropy is proportional to surface area, specifically the area of the event horizon. This is called the Bekenstein-Hawking entropy, and it's a precise mathematical relationship. The entropy of a black hole equals 1/4 of its horizon area, measured in units of Planck length squared. This is strange. Why would the information content of a three-dimensional object scale with its two-dimensional surface area instead of its volume? This suggests something profound. Maybe the information isn't actually inside the black hole. Maybe it's somehow encoded on the event horizon itself. This leads to what's called the holographic principle, which is one of the most radical ideas in modern theoretical physics. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that region. Just like a hologram encodes a three-dimensional image on a two-dimensional surface, the universe might encode the full information content of a region on its boundary. For black holes, this means the information about everything that falls in doesn't disappear into the singularity. It gets encoded on the event horizon. The horizon acts like a cosmic hard drive, storing every bit of information about every particle that crosses it. From the outside, we can't read this information easily, but it's there, preserved in the microscopic structure of the horizon. This isn't established physics yet. This is where we transition from well-confirmed theory to active research and speculation. The holographic principle has strong theoretical support from multiple independent lines of reasoning, particularly from string theory and from a precise mathematical correspondence between certain gravitational theories and quantum field theories in one fewer dimension. But we don't have direct experimental confirmation, and we don't have a complete theory of quantum gravity that would give us the full picture. What we can say is this: if the holographic principle is correct, then black holes don't destroy information, they hide it. Everything that falls into a black hole leaves an imprint on the horizon, encoded in ways we're still working to understand. The horizon itself might be made of fundamental quantum degrees of freedom, tiny units of area each carrying one bit of information. When something falls in, it doesn't vanish. It becomes part of the horizon's information content. But this raises new puzzles. If information is preserved on the horizon, how does it get out when the black hole evaporates through Hawking radiation? The radiation initially appears to be completely thermal, meaning it carries no information, like random static. For information to be preserved, the radiation must eventually become non-thermal, carrying subtle correlations that encode what fell into the black hole. This is called the black hole information problem in its modern form, and it's still being actively researched. Recent work suggests the radiation does become non-thermal, but only after the black hole has evaporated past a certain point, roughly halfway through its lifetime. Before that, the radiation is essentially random. After that, it starts carrying information out. This requires extremely subtle quantum correlations between the radiation emitted at different times, correlations that would be impossible to measure in practice, but which exist in principle and preserve unitarity. There's also the firewall paradox, which emerged from trying to understand how this information transfer works. If radiation is entangled with the black hole's interior in the way required to preserve information, but also entangled with previously emitted radiation in the way required by Hawking's calculation, you get a contradiction because a quantum system can't be maximally entangled with two different systems simultaneously. One proposed resolution is that the event horizon isn't smooth and empty, as general relativity suggests. Instead, there might be a violent energetic barrier right at the horizon, a firewall that destroys anything trying to cross. But this contradicts the equivalence principle, which says freely falling observers shouldn't experience anything special at the horizon. These are open problems. We don't have consensus solutions. Different approaches to quantum gravity suggest different resolutions. String theory, loop quantum gravity, and other frameworks all offer pieces of the puzzle, but none gives us a complete picture yet. What they share is the recognition that information must be preserved somehow, even if we don't fully understand the mechanism. Let's think about what this means more broadly. If black holes encode information on their horizons, and if the holographic principle extends beyond black holes to the universe as a whole, then everything we think of as existing in three-dimensional space might actually be encoded on a two-dimensional boundary. The universe itself might be a hologram, not in the sense of being fake or illusory, but in the technical sense that all the information about what happens in a volume is stored on its surface. This doesn't mean we're living in a simulation or that reality isn't real. It means the fundamental description of reality might be lower dimensional than our experience suggests. Just as a hologram looks three-dimensional but is actually encoded in two dimensions, the universe might look three-dimensional but be fundamentally described by information on a two-dimensional boundary. This has profound implications for how we think about space-time itself. If space is emergent from quantum information, if geometry arises from patterns of entanglement, then space isn't fundamental. It's derived, like temperature emerging from molecular motion. The fundamental reality might be quantum information, relationships between bits, and space-time is what this looks like when you step back and view it macroscopically. Black holes are the testing ground for these ideas because they're the most extreme objects we know of, the places where gravity and quantum mechanics collide most forcefully. Understanding what happens to information at a black hole horizon might teach us something essential about the nature of space-time, information, and reality itself. Here's another way to think about it. When you look at a black hole from the outside, you never actually see anything cross the event horizon. Due to gravitational time dilation, as something approaches the horizon, it appears to slow down, redshift, and fade away, asymptotically approaching the horizon, but never quite reaching it from your perspective. In a sense, everything that ever fell into a black hole is still there at the horizon from the outside perspective, frozen in time, encoded in the horizon structure. From the perspective of the infalling object, it crosses the horizon in finite time and continues toward the singularity. These two descriptions seem contradictory, but they're both valid in their own reference frames. This is called black hole complementarity, the idea that different observers can have different but equally valid descriptions of what happens, and that there's no observer-independent fact of the matter about whether something is inside or outside the horizon. This sounds like it violates basic logic, but it's similar to how relativity of simultaneity works in special relativity. Different observers moving at different speeds disagree about whether two events happen at the same time, and there's no absolute answer. Both observers are correct in their own frames. Black hole complementarity extends this idea to the question of whether information is inside the black hole or encoded on the horizon. Both descriptions are correct, but they apply to different observers who can never compare notes because one is inside the event horizon and can't communicate with the other. Again, this is speculative. We're pushing at the boundaries of current understanding. But these ideas emerge from taking seriously the mathematics we have and trying to resolve contradictions. They might be wrong. Future developments might show we were thinking about this incorrectly. But they represent our best current attempts to reconcile quantum mechanics and gravity in the extreme environment of a black hole. What's clear is that black holes are far more than simple cosmic vacuum cleaners. They're laboratories for testing fundamental physics, places where our theories are pushed to their limits and beyond. They reveal tensions between quantum mechanics and gravity that we can't ignore, and they suggest that information, rather than matter or energy, might be the most fundamental currency of the universe. If information is never destroyed, if it's always preserved in some form, then the universe has a memory. Everything that ever happened, every particle that ever existed, every configuration of matter and energy throughout cosmic history leaves a permanent record. Not in some mystical sense, but in the physical structure of reality itself. Black holes don't erase that record. They compress it, encode it, preserve it in ways that challenge our classical intuitions but respect the deeper quantum laws. This brings us to philosophical territory that physics alone can't fully address. If information is fundamental and indestructible, what does that mean for concepts like creation and destruction? Nothing is truly destroyed in the sense of being erased from existence. It's transformed, encoded, preserved in new forms. The universe doesn't forget. It might hide information, make it inaccessible, scatter it across horizons or in Hawking radiation, but it keeps it. Some physicists find this idea beautiful, suggesting a deep order and consistency to nature. Others find it puzzling, wondering what it means for information to be preserved if it can never be retrieved. If information is encoded on a black hole horizon in a way that's scrambled beyond any practical recovery, does it matter that it's preserved in principle? These aren't questions physics can answer definitively, because they depend on what we value and what we mean by meaning, but they're questions physics forces us to ask. By studying black holes, by working through the mathematics of quantum gravity, we're learning that the universe operates according to principles that transcend our everyday experience and intuition. We started with a question about destruction. Do black holes destroy what falls into them? The answer appears to be no. They hide it. They encode it. They preserve it in forms we're still learning to understand. This isn't the final answer. We don't have a complete theory of quantum gravity yet. We don't fully understand how information gets out during evaporation. We don't know if the holographic principle is exactly right or needs modification, but we do know that the simple picture of black holes as destroyers of information is wrong. Something more subtle and more interesting is happening. Black holes might be the universe's way of compressing information to its theoretical maximum density, storing it on two-dimensional surfaces while maintaining the illusion of three-dimensional volume. They might be telling us that space itself isn't what we think it is, that the familiar geometry of our experience emerges from quantum information in ways we're only beginning to glimpse. This is frontier physics. This is where we are right now, working with pieces of theories that we know are incomplete, trying to fit them together, guided by mathematics and physical principles, but aware that we might be missing something essential. It's humbling and exhilarating at the same time. We've learned enough to know that our old pictures were wrong. We haven't yet learned enough to be confident the new pictures are right. What we can say with some confidence is that black holes are not endpoints. They're not erasers. They're transformers, repositories, cosmic archives storing everything that touches them in quantum codes written on their horizons. They don't destroy the universe. They hide it, compress it, preserve it in forms that challenge everything we thought we knew about information, space, and time. If that leaves you with more questions than answers, you're in good company. The physicists working on these problems have more questions too. But that's not a problem. That's the process. That's how we make progress. By following the mathematics, respecting the experiments, and being willing to abandon our intuitions when they conflict with what nature actually does. The universe is under no obligation to make sense to us, but it does seem to follow consistent laws, and those laws, when we work them out carefully, reveal a reality stranger and deeper than we imagined. Black holes are one window into that reality. What we see through that window suggests information is more fundamental than matter. That space might be emergent, and that nothing is ever truly lost, only hidden in increasingly subtle forms. If you want to keep exploring these ideas, there's much more to discuss. The relationship between entropy and information, the nature of time, the possible connections between quantum entanglement and spacetime geometry, all of this branches out from the black hole information problem. Consider subscribing if you're ready to keep going deeper. The universe rewards careful attention.